Okay, so exam 1 is next Monday. On our Canvas website, I believe I have formulas. Did y'all? Has anyone seen the formulas that I have on? It's just like 7 pages of formulas. It's the same as what's in the back of the book. Yes. Can I see that real quick? Make sure that is what it is. Yeah. This is it's all these formulas from the back of the book. It's reference pages 1 through 6. You can have that on the test. You have to print that out yourself and bring it though. All right. So there's not a question of, oh, you know, I'm not going to have basic geometric formulas and trig identities. That's all there. Okay, you can have that. In addition to that, okay, the formula sheets. I will also allow you to have, how about 2 pages of notes? And that means no worked out problems. When I say 2 pages, I mean 2 physical pages. You can write on the front and back of each one. So a total of 4 faces of the page, right? And you can put things like, you know, if I'm given 2 planes and I'm asked to find the line of intersection, then I should cross the normal vectors of the planes and then find a point on both planes. Right? You can write yourself all the steps and give yourself hints. You just can't work a problem out. Okay? I'm pretty sure the test is going to be very long. Yeah, it'll depend on you. I would say it's probably going to be at least 2.5 hours. Yeah, because the final is the same way. The final is 3.5-hour test. The midterm, I want to treat it the same way. Yes, I haven't made it, so I don't know. But what I will do is I'll throw out what I gave on my exam last semester, spring. I'll post that out on Canvas for you. Just give you an idea of what I asked. It turned out that I think the exam I asked last spring, the problems were directly from the book and right out of the book. So. There were 13 on this one. These are just the solutions to it. So I already have the answers and the tests made up from last semester that I could share with you. And I don't mind sharing exams with you so much because I redo the exams every semester, so it's not that big of a deal. So I'll send that out later on today, okay? They were similar to the homework problems, yeah. I would just wait until I send it out, take a look at it, and then if you have additional questions on Wednesday, we can talk. Okay. The exam, anything else about the exam? Did I answer all your questions? It's going to stop at 11:07, which is what we're going to try and get to by the end of next class. Right now, that's what we're saying. 11:07 is what it will go through. So through 11.7, unless I tell you otherwise. Any other questions on the exam in a week? Okay, the exam that you just took, the first mini exam, The grades for those, where the hell did I put that? I had a little index card with the grades on them. I don't know. I think I remember what it was. I know what the class average was. Class average was a 74. The standard deviation was a 17. I believe there were 5 A's. I believe there were 3 B's. I believe that there were 6 C's. I want to say 5 D's and 3 F's. I want to say that's what it was. The highest grade was 100. I don't remember what the lowest grade was. There was a bonus. I don't recall if it was a 5 or a 10-point bonus. Remember I said if you turn it in on that Monday, I'll count it bonus. You turn it in Wednesday, no penalty, right? So let me pass these back. Every problem was graded out of 25. I believe there were, there were 5 problems. So 20 points each. I just graded them all equally. And the most commonly missed problem was, I think, the one where you had to, number 3, where you had to find the values of B which make these 2 vectors orthogonal. And the reason why most people lost points is because I said you couldn't use a calculator or a computer or anything like that. So people would, I'm not sure how people would do it, but they would just give me the correct answers, but there was no work to support it. So if that was the case, I took off a lot. If you want to come and argue, not argue like argue, but if you want to come defend your work, then I don't mind sitting down with you if you can explain to me how you got it, okay? But not like in 2 weeks, like it needs to happen very soon. All right, so I'll just call your name. Raman? How do you say your last name? Raman? Okay. The grade, there is no grade on the test. You just have to add up the points and subtract from 100. Hernandez, David? Martinez? Dorado? Martinez? No. Evans? Zamora? Stanton? Sanchez? Okay. Singh? Mora? Stephen? How do you say your last name? Chamu? Okay, that's what I was going to say. I didn't want to mess it up. Okay, Booth? Lee? James Lee? And we can talk more about what our email conversation. I was trying to figure out who you were first before. Yeah, okay. So we'll talk more. Bustos? Austin? Watson? Farham? I say that right? Okay. Castilian? Castillon. Trying too hard. Okay. Martinez? Rolando? Clay? Lansdale? And Heisenberg. Like the Heisenberg uncertainty principle, kind of? All right, almost. Not spelled the same, but pronounced the same? Heisenberg. Okay. Gonzalez? Evan? Allen? Austin Anderson? Let's see, Mr. Anderson? Alan? Evan? Okay. Yes. Right there. Yes. Okay. Well, as opposed to what? Like, no computers? How did you do it? Okay. Well, a calculator is a computer. Right? Yes. Hmm? Yeah, you know what? If you have a specific question, I'd be happy to entertain questions about anything on the test. Just after class, let's talk. Okay? Because if I have to address everyone's individual questions, I'll be here all day. All right, we finished up, or did we finish? We were doing partial derivatives last time, right? And we ended it with that note right there. We were talking about notation. So there's all these different notations when it comes to partial derivatives, and it depends really on kind of the author that, which notation they are going to use. And then we did not look at this, but just like with derivatives, we have this concept of second derivatives, third derivatives, so on and so forth, right? So how do we say second derivative when you're looking at partials? So here's all the different notations of how you could say the second derivative. So this inside the parentheses here, that means partial derivative, right, of f with respect to x, and then an x on the outside of that means now do it again with respect to x. And then you could write it this way, xx, or you could write 1, 1, or this, or this, or this. So I'm not going to go through all of these. What I do want to point out, though, is this one right here. If you write down partial of f with respect to x, and then a y on the outside, what do you do first? You take the partial with respect to x first. And then, after you do that, the partial with respect to y. Now, look, if you remove the parentheses, and this is the notation you're going to see mostly in this class. If you remove the parenthesis, you're going to have to remember that the partial that you do first is the one that's closest to f. So you do that one. So it's almost like you read it left to right. So partial with respect to x first, then after that with respect to y. And then notice down here, if you want to do the other direction or the other order, you do it this way. Okay? Questions? Now, you could extend this out and have third partial, right? You could have like, do it with respect to x, and then do it with respect to y, and then do it with respect to x again. Or you could go x, y, y, right? Or y, y, y. It just, you can have as many derivatives as you possibly want. So look at this one. Find all the second partial derivatives of this function. Find all the second partial derivatives. So my function is f of xy equals x squared plus 4y to the fifth minus 10x cubed y squared. So let's first list out what are the possible partial derivatives. What second partials? I could have f xx, right? I could have f, how about xy. I could have f yx. I could have f yy. Are there any other possibilities? If I'm only limited to two partials, right? When we say second partial, we mean we're only allowed to take the partial twice. Is there any other combination I could have? Okay, are these two the same? No, not necessarily, right? They might be. You may have a function that turns out that those two are the same, but in general, they are not. So let's just go through these one at a time. If I'm going to do this one, then the first thing I'm going to do is just find what the partial with respect to x is, which is what? So we look at x squared, derivative of x squared with respect to x means I treat x like a variable, treat y like a constant. So derivative of x squared is just 2x. Derivative of 4y to the fifth, 0, because all that's a constant, right? Over here, the y squared is like a constant with the 10, right? So I just really need to take the derivative of x cubed, which is the 3 comes out, right? Hits the 10. So negative 30. Can I say x squared, y squared? Yes? Any questions on that? And now to get the second partial, I just take the partial of that again with respect to x. So I do, what's derivative of 2x? It's just 2. And then over here, let's see, 2 comes out. So negative 60xy squared. That is your partial with respect to x twice. Let's do partial with respect to x, then y. Well, I already know the first part, don't I? I already did the partial with respect to x. That's this right here. So all I need to do now is take the partial of that with respect to y. Do you agree? So what's the partial of that with respect to y? So what's the derivative of 2x with respect to y? 0. Then over here, y is my variable, so all this negative 30 x squared is a constant, so derivative of that should be what? Negative 60 x squared y. Good. Questions? What next? You want to get fyx or fyy? It doesn't really matter which one we do first, does it? How about partial of f with respect to y twice? Well, first I need partial with respect to y. So go back to the original function. What's the partial of this with respect to y? Well, derivative of that's 0, right? X squared. Derivative of this is going to be 20y to the fourth. And then this one, negative 20 x cubed y. So we just took that 2, dropped that 2 down. The x cubed stay there. Let's go partial with respect to y again. So 80x cubed, or sorry, 80y cubed. Then what? Minus 20x cubed, because the derivative of y is going to be 1. Questions on that? So the test on Monday, how about just I give you like 10 of these problems? That would be great. How about fyx? So I already have the partial with respect to y, right? So now what's partial of this with respect to x? So the derivative of this is 0, right? Because x is my variable now. So I just need the x cubed. 3 comes out. So what do we get? Minus 60 x squared y. We have all 4, don't we? Y'all all right with those? Questions? Just so we'd be clear, if you were to try to find all the third partials of a function, then how many third partials could you have? So you have fxx, right? You could have fxxy. You could have fxyx, right? You could have fxyy. Are there more? Right, you have y's in the first one, right? So there's all these different variations. So looking for all the second partials is good because there's only, what, 4? But if you go to third partials, it increases, and then fourth. And what does it look like it is? Like, is there a formula to know how many there are? Let's see. Let me list out. F, Y, Y, Y. How about F, Y, X, Y, F, Y, Y, X? Am I missing any here? XX? Are there any others? I'm with you. Hold on. Did I miss any? Did I repeat any? It looks like there's 8 of them, right? So when I asked for second partials, there were 4. When I asked for the third partials, there were 8. So it looks like for the nth partials, it might be 2 to the n. So maybe if you look at all the fourth partials, there might be 2 to the fourth, many of them. That's a pattern, right? Now you'd have to prove it, and you'd have to convince yourself. But this is more of like permutations and combinations, the problem, than it is anything more than anything else, right? Do y'all see that? It's just a basic statistics problem, or probability and statistics problem. It's like a combination lock, right? If I have 3 slots for a combination lock, and this can be one of 2 things, right? It can be an X or a Y, and this one can be an X or a Y, and this one can be an X or a Y. Then there's 2 times 2 times 2 ways to do that, right? 2 to the third. All right. Next, we have a theorem. Clairaut's theorem. If f is defined on a disk, D, that contains the point x0, y0, and if the partial of f with respect to x then y, and the partial of f with respect to y then x, so that's reversing the order there, are both continuous on D, continuous meaning when you take those partials, those second partials, when you take them, the answer is a nice, well-defined function on that disk, then the partials will be equal. This is a theorem. We'll use that later, possibly, so just keep that in mind. All right, so here's an example of a problem where I ask you to find what, a fourth partial here and then a third partial here. I think we don't need to do that. Would you agree? It's just really to show you the notation. On this first one right here, A, you would do the partial of this with respect to x. Then you would take that answer, do the partial with respect to y. Then take that answer, do the partial with respect to y again. Then you do that answer and do the partial with respect to x. And then you'd be done. Well, this right here is just to show you, to make sure you're clear on the order in which this is saying to do things. It's not necessarily going to apply to much at this point. What will matter is the second partials when you have f with respect to x then y, and then y then x. Those will matter because that's going to help us. If you remember back, we might be getting ahead of ourselves here, but back in Cal 1, when you wanted to find the maximum of a function, you did what was called the second derivative test for concavity to figure out if you were concave down or concave up at a point. And if your first derivative was 0 and your second derivative was negative at some point, then you would know that you were at a local max, because you would have flat horizontal tangent line and then concave down. Second derivative meant concave down, or second derivative negative meant concave down. Then you know you're at a max. We're going to have something like that for surfaces. We'll be using the second partial to help us determine that. I hope that addressed your question. Okay, so this is just an example of something called Laplace equations. This will happen in some physics class. Different places you might run into a Laplace equation, and there's plenty of other different types of equations. But this is just an opportunity for me to share with you how some partial derivatives are used in application. So if you have a function, u is a function of x and y. So you have a function of two variables. We're calling it u instead of f. All right. Then if the partial of u with respect to x, and then with respect to x again, plus the partial with respect to y, and then with respect to y again, if that equals 0, then this is called a Laplace equation. All right, this functions which satisfy this equation are used in mechanics, heat dynamics, fluid flow, electric potential problems, et cetera, et cetera. So let's say we're given this function of x and y, and we are asked to determine if it is a solution to the Laplace equation. So is that function a solution? That's kind of weird. Look, we are saying that a function that satisfies this equation is a solution to the Laplace equation. So your answer is actually the function itself. Don't understand? We have an equation. The solution to this equation is a function. We're being asked, is this a particular solution to that equation? So all we have to check is what? Those partials, right? So uxy equals... How many of you have seen Laplace equations somewhere? Anyone seen Laplace? 2? Physics? Yep. If the what? Well, the second partial plus of x plus second partial y is 9x. So could you say that that's 0 if x is equal to 0, or is 9x not equal to 0? Well, hold on. Let's get them first. What we're trying to check is this, right? We want this. We want to know if this is true, right? That's the question. Is that true? Well, what's the partial of u with respect to x? Let's just get the first partial. That's 3x squared, right? Plus what? 3y squared. Now take the partial of that again with respect to x, and what do you get? 6x plus nothing, right? Okay. Now, over here, we also need to know what the partial with respect to y is. So what's the partial of that with respect to y? Up here? We get 6xy. Agreed? What's the partial of that with respect to y again? 6x. When we add these two together, do we get 0? No. Right? You get 12x. So is this function a solution to the Laplace equation? No. That's it. Now you're asking, well, if x is 0, but then if x is 0, then the function itself is the 0 function. And the 0 function would always satisfy the Laplace, but it's trivial. So it's a trivial solution. Understand? So, I mean, it's kind of dumb, but if this would have obviously turned out to be negative 6x, then it would be a solution, wouldn't it? Okay. The idea is just that you understand what it is you are checking. Do those both add up to be 0 or not? Well, you have partials with respect to a variable twice. So it's almost like you want to know the rate at which u is changing with respect to x. And then the second partial should give you almost like a concave, right? Like concavity check, but only in one direction. And then the other one is the same thing in the other direction, so a concavity check. And you're wanting to know if those add up to be 0, which means they cancel each other out, right? Now, I mean, the way you can apply that to, I mean, what that would mean physically in different scenarios would depend on what it is you're looking at. Do y'all remember how y'all used them in physics at all? Wave equations? Okay, so it all depends on the application. I mean, I don't know if that answers enough. I don't want to get into a specific example. It would be kind of hard to just throw a physics problem in here. I mean, all we're going to do is, what we want to do is be able to understand the mathematics of what we are doing there. You know, if your function satisfies the Laplace equation, that's what you have to check. Once you have that, then all the consequences of what Laplace solutions can do for you depend on the field. I'm kind of waving my hands at your question. Okay, let's see here. That we already checked. Implicit differentiation. All right. Things get a little bit weird here now. All right. Implicit differentiation. So before I begin this, let me go back and take a look at something from Cal 1. All right, if you were asked in Cal 1 to find dy dx, all right, if you were asked to find that, then what would you do? Get y on one side of the equation? Well, what if you can't? Because this equation you cannot isolate y. Right? Y is trapped inside the cosine, so you can't get it out of there unless you do arc cosine, but then you trap the other one in arc cosine. There's just no way to isolate it. So we used implicit differentiation. And so what we did is we said, we just look at this entire equation, and we just take the derivative on both sides with respect to x. On both sides of the equation. So when I look at the left side, I say, all right, I have a term over here, and then I have another term here. So whenever we take the derivative of the sum of two things, we just do derivative of each one, right? The derivative of the first one, I notice I have a product right there, right? So I do product rule on that. What is the derivative of x squared with respect to x? Because that's what we're saying, with respect to x. What's the derivative of x squared with respect to x? 2x. And then product rule then says times the other function, right? Don't do anything to it. Then plus, now the derivative of the other function. What's the derivative of y with respect to x? That's what you want to know, right? dy dx. Or you could say y prime, depending on how comfortable you are with the notation. And then finish off the product rule, it would be what? Times what? X squared. Does everyone see that's the product rule on that first piece? And then you'd move on to the next one. You say, okay, and here I've got cosine of something. So chain rule would tell me I first need to take derivative of cosine. Derivative cosine of something is negative sine, so I'm going to change that to a negative sine of whatever's in there. Then chain rule says times the derivative of what's inside. Well, derivative of what's inside is a sum, so I can just do derivative of each one separately. Derivative of x is 1 with respect to x, right? So, and then the other one is plus derivative of y with respect to x, which would be dy dx again. And that would finish off the left side, wouldn't it? And then we have equal 0. And then what you would do is you go about trying to isolate that term. So you just algebraically manipulate things and move things around, get all your dy dx on one side, and then you would have your derivative, right? Okay, that's what we did when we had an equation with two variables in it, right? We would treat one as being dependent on the other, correct? Treat one as being dependent on the other. Here, y depended on x. So when we took the derivative of x, it was always 1, right? Or if we took the derivative of x squared, it was 2x. But when we took the derivative of y, we said it was dy dx, didn't we? What happens now if we get an equation with 3 variables instead of 2? How can we take derivative? So that's what this section is about, or this last part of this section is about. So let's take a look at this one. It says, given this equation, find the partial of z with respect to x, and then find the partial of z with respect to y. Now, what does this mean? I want to know the rate at which z is changing with respect to x, treating x like my variable, right? Yes? And then the partial of z with respect to y means that I want to treat z as if it depends on y, right, instead of on x. How is that going to change the two? And then what do you think we're going to do with the other variable? Like in this one, I have the z and the x here, but what are we going to do with the y? Constant makes sense? I mean, we said partial derivatives, you hold one variable constant, don't you? Okay, well, let's work through it. We have x cubed plus y cubed plus z cubed equals 6, not equal, plus 6xyz equals 1. First thing we want to find, what is the partial of z with respect to x? So I will stress to you again that whenever we do this, we want to hold y constant, don't we? Hold y constant. So let's take some derivatives here. What is the derivative of x cubed with respect to x, right? Back over here, remember this whole thing is with respect to x. So x is our variable. We're assuming z depends on that x, and we're holding y to be constant the whole time. So what's the derivative of x cubed? 3x squared, just like it was in Cal 1, right? Because it's with respect to x. So this is going to be 3x squared. Plus, what's the derivative of y cubed? That's going to be 0, right? Now, let me show you something, just so you can see this. Technically, the derivative of y cubed is actually 3y squared times, chain rule would say then y prime, right? Or here we can't use y prime, we have to use partial of y with respect to x. That would be the technical thing that's happening here. In fact, next to the, I'm trying not to confuse you, but next to this right here is a partial x with respect to x because of chain rule. But what's the partial x with respect to x? That's 1. Here, what's the partial of y with respect to x? So I'm asking you, how much does y change when x changes? Well, if we hold y constant, y is not changing. So that change is 0. So that little change is always 0, so it always kills off everything else. That's why it's 0 to begin with. But there's a thing later on, if you go on and take more math, there's a thing called the total derivative, where what you do is differentiate everything, and you don't assume anything's held constant, and then you can come in later and you can plug in all, what's being held, what's not. But the total derivative assumes everything's a variable. But we'll just say 0. Okay, plus, now, what is the derivative of z cubed? So z's not held constant, right? We're assuming z depends on x. So we're going to say power rule, 3z squared. But then chain rule tells us the derivative of the base, which was the derivative of z, with respect to x. So I put partial z with respect to x. Now, is that 0? No, that's not 0 because, well, hell, that's what I'm trying to find, right? So it's actually appeared in the problem finally. And then plus, what do we have here? We have to take derivative of this, don't we? How many variables do you see there? Technically, there's only 2, right? I can split it right down the middle like that and look at it like a product rule. What is the derivative of 6xy if I'm treating y like a constant and x is my independent variable? What's the derivative of the x become? 1, right? So that just becomes 6y. Y'all follow that? So I'm doing product rule, 6y times, finish off, or do the rest of product rule, z plus, now you have to do derivative of the other one. What's derivative of z? Partial z with respect to x, and then finish off product rule times 6xy. Am I done with that? Equals what? 0. So when you look at this, as you can see here, I've got the partial of z with respect to x. It appears in two places. So I could algebraically manipulate things around, move things around, isolate that out, and then be done. Questions? Now, how would that differ from the next one, partial z with respect to y? So let's do the same problem here. I'll do it right underneath. What's the derivative of x cubed? That'll be 0. And now instead of derivative of y cubed being 0, it's now 3y squared, right? Anything different on the z cubed? Well, it's still 3z squared, but now partial z with respect to y instead of x, right? How about that product rule? What changes here? We still have to do a product rule, right? Still have to do a product rule here? X is my constant now, isn't it? So what's derivative of this over here if x is constant and y is my variable? 6x? Okay, so we get 6x and then times z and then plus partial z with respect to x, or no, y, sorry, times 6xy equals 0. So pretty similar, right? There's some subtle differences in there, right? Little differences, but overall it's the same kind of format. Questions? All right, let's move on. I'll put the homework assignment up for you later on. See if I can find 11.4 here. Tangent planes. There's some formulas in this section, all right, that we need to remember. This is one of them. Remember I said that if you have a surface, we want to talk about a tangent plane instead of a tangent line? Remember that? It turns out that if z is a nice continuous function, right, if it has partial derivatives, that means you can take the partials and they exist and they make sense, they're nice defined functions, then the equation of the plane, which is tangent to the surface at a point x naught, y naught, z naught, is this. Now, remember what the equation of a plane is. Remember the general equation of a plane? A times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Remember that? That was the first time we talked about the general equation of a plane. The ABC, right, was a vector. What vector was that? That was the normal vector, wasn't it? So those numbers in front of the x, the coefficients of x, y, and z were the components of our normal vector. Well, if we're saying that this is the new equation of the tangent plane at some point x naught, y naught, z naught, then the A is this, isn't it? The B is this. And what is the C? Always -1. That's what the conclusion of this is that in order to figure out the equation of that tangent plane at a point, all you need to know is the partial derivative with respect to x, evaluated at the point you're given, partial with respect to y, evaluated at the point, and then that C part, the C, that part in front of z, will always be -1. So that's the normal vector of the tangent plane. It's a nice result because it gives us a way of finding tangent planes anywhere on a surface, as long as it's nice and defined. So how about this one? Find the equation of the plane, which is tangent to this surface at this given point. So f of xy is 1/2 xy. We're looking at the point 1, 2, 1. So let's first be sure we're clear that this really means z is equal to 1/2 xy, right? Our function, right, is we could replace f of xy with z. The 1, 2 zeros are x naught, y naught, z naught. And so what we're going to need is some partials, right? What's the partial of this thing with respect to x? Half y. What's the partial of this thing with respect to y? Half x. So if the formula is this, it's a lot to write out here, but I'm going to do it. All right, that's the equation we have. What does this first part mean, right here? What does this mean? So I take the partial with respect to x, and then what does this mean right here? Plug in the x naught and y naught. So plug in 1 for x and 2 for y, right? Well, look, the only thing that appears in my partial is y, right? So I just plug 2 in for y. So when I take that and I say, what's the partial with respect to x at 1, 2? The answer is 1/2 times 2, which is 1. And that part is this, right? That's a 1. And then I have x minus x naught. I'll take care of that in a second. Let's find this part. What's the partial with respect to y at 1, 2? 1, 2 is equal to 1/2 times 1, which is 1/2. So that part is this. And everything else just plug in, right? I mean, this whole problem breaks down just taking some quick partials, plugging in the point, and then plug into this equation. So what do we have? What's our equation? 1 times x minus 1 plus 1/2 y minus 2 minus 1 times z minus 1 equals 0. Then you could clean it all up. Did y'all watch that game yesterday, the U.S. game? Yeah. So I'm sitting there, and I had been down in our backyard swimming and watching the game outside, and the first half sucked, so I came up, and when I came up, they scored a goal, and so it was tied, and then I was watching, I was all into it. We scored, we went up, and then we were in that last 30 seconds of the match, and my wife comes in and is like, hey, who are you for? Like she has no idea what the hell is going on. Who are you for? And as soon as she said that, he crossed it and had the header, and I was like, no. And yeah, I was all upset. I'm like, talk about bad mojo. She brought it into the room, I know. Oh, man. Okay, so I'm going to distribute this through, and who are you for? What do you say to that? So distribute, right? No, that's not right. No, it is, right? Okay. Sorry, my brain is definitely not here right now. This is just to get a nice version of the plane. Y'all agree? So if I graph this plane, it should touch this surface at this point, and it should be tangent to it. We should talk a little bit about that, though. I mean, what does it mean to be a tangent plane? And maybe something you should consider is back again in Cal 1 or Cal 2. When we have a curve right, like this. If I were to say, look at this point, let's say right there. A tangent line at that point just barely touches, right? Just goes through one point, right? Kind of balances on that. But doesn't mean that that tangent line cannot hit the graph anywhere else. And look, if you extend that line, doesn't that line punch through the graph over here again? So a tangent line isn't a point that only touches a curve at one point and nowhere else. Some curves are impossible for that to happen. So same thing with the tangent plane. We're saying at that one point, it's kind of balancing through, just crossing through one point on our surface. It's like the best plane we can find that does that, right, at that point. And yes, somewhere else it might cut through the surface, but at that point is where we're interested in. Yes? Do you see kind of difference? It's hard for me to draw it in 3 dimensions, but just keep that in mind. Here's the actual thing we just did. So if I come over here, everywhere on this graph, there is a tangent plane. See how I'm saying, like at that point, it's the best approximation, even though it's cutting through the plane in different places? Does that show you enough for you to understand what a tangent plane is, like geometrically? Do you see it? That at every point I should have some tangent plane? It's not arbitrary. And then right there at that point right there, it looks like we get a flat, like a plane that's parallel to the XY coordinate plane, right? So our answer was that one right there. And I believe that's the equation right there of that plane. Okay, find the equation of plane which is tangent to the surface. Z equals f of xy equals arctan xy squared at the point 1, 1 pi over 4. So this is the same exact thing we just did. The only difference is that the derivative is a little more interesting. That's it. So let's make sure you can take that derivative without any problems. Z equals arctan. That's the same notation for arctan, isn't it? I'll use that notation just so you can see it's the same. All right. What is the partial of f with respect to x? Because I'm going to need that. So what's derivative of arctangent of something? 1 over 1 plus whatever was there squared, right? So for us, it's actually going to be xy squared squared. So if you need to go back, review the derivative of arctangent of u is 1 over 1 plus u squared times u prime. That's our derivative of arctangent. So we're still missing the derivative of what was in there. So what's the derivative of what was in here? Well, with respect to x, right? So it's what? Y squared. So we really have y squared over 1 plus x squared y to the 4th. Is that okay with you? Just do it like that? Okay, that's our partial with respect to x. Now, we may as well get our partial with respect to y. Shouldn't that be the exact same thing as far as this portion of the derivative? It's exactly the same? It's just the difference is the derivative of what's up here with respect to y. So what's the derivative of that with respect to y? 2xy? And that'll be on top instead. So I'll have 2xy over 1 plus x squared y to the 4th. And now, don't I need to evaluate both of those at the point I was given? The point I was given was 1, 1 pi over 4. I'll write that down over here. 1, 1 pi over 4. So what is this one at 1 pi over 4? 1 over 2? 1/2? And what's this one at 1 pi over 4? 1? 2 times 1 times 1, that's 2 on top, and then you get 2 on the bottom, so you get 1. That's all I need, right? I have the partials evaluated at the point. I have the point itself. I can write the equation of the tangent plane. So we should have, what comes first here? 1/2, and then x minus x naught was 1, then plus 1, and then y minus 1, and then plus, oh no, not plus, it's always what? -1, and then z minus pi over 4. We'll see later why that's always -1. For now, just take it on faith, okay? We're going to have actually an even more general formula than this later on. This is just the same thing, showing how that's the surface, kind of cool looking surface, right? That's what arctangent of xy squared looks like. If I show the plane, oh, there it is. And we just found the solution to be there it is, right there. That's our solution plane. Now, why did we say this was useful? I mean, maybe it's not. Where is it that we have maximums and minimums? If you had a surface, where would, tell me about the plane, the tangent plane, if you were at like a maximum. It would be parallel to the xy x, so the equation of it would, what would be happening there? Your normal vector would have to be what? Pointing straight up or straight down, right? Agreed? Pardon me? If you are a horizontal plane, then your normal vector is pointed straight up or straight down. Right now, it might have different lengths to it, but they always have to look a certain way. All right, so we'll address that later. Okay, well, that's it for 11.4. There's nothing more there that we need. Is 11.5 on our schedule? It is? Chain rule, right? Is chain rule printed out in there for you? Okay. I don't think I have the chain rule notes up here that I can project. I'll double check right now, but I don't think I do. You know what? While I'm pulling it up, go ahead and hit the middle light. I'm going to pass out your. I'm going to pass out up here. No, I'm going to pass out your next mini exam. I'm not sure if that's the correct homework. Yeah, so I wouldn't go off of that. Okay, let's talk chain rule. Is everyone looking at 11.5.1? Remember that back in Calculus 1, right, is when you did chain rule? If you had a function y that or an equation that related y to x, and y could be determined directly from x, then we had the concept of the derivative, and we'd write dy dx, right? I mean, that was the first thing you ever learned when it came to derivatives. And then I gave you this example, 11.1, example 1. What is the derivative of y equals x squared plus 6x minus 3? Just 2x plus 6, and we're done, right? Nothing to it. The only thing I want you to see right now is that y, right, is equal to something that has x's in it. So y depends strictly on x. It's the derivative we grew up with, right? Now, with chain rule, I'm at 11.5.2. What we said is that if y depended on some variable x, and that x variable depended on some other variable t, then we could find the derivative using chain rule. And then I have the chain rule from Calculus 1 written there. And then let's look at this example. I'm at example 2 already. So look, let's say y was equal to sine squared t. I'm going to write it like that first. Can you all see that all right? You could come in here and realize, look, y is equal to something squared, right? I'm going to call it x. And the x that I'm talking about is actually sine of t. Y'all agree? Then I can say that dy dt is dy dx times dx dt. And I hope all of you have done chain rule so much that you wouldn't have to write that out, right? You wouldn't break that down. If I gave you that, you could take derivative of that and just say, oh, it's just 2 sine t cosine t, or just, what, sine 2t, right? Hopefully. But do you remember how we did this, like how this came about? So y is dependent on an x, x is dependent on a t. That's a picture, right? Y dependent on t, on x, x dependent on t. If y depends on t, then there's a derivative between the two, right? If x depends on t, there's a derivative between those two also. So what we had was dy dt here, or dy dx here, and dx dt here. And then when we multiplied those two together, right, multiplied them, you get this. This section is very visual, so I want you to see that I've created like this diagram and how my variables are connected to each other, and then how the derivatives exist between them, and then how we get the chain rule by multiplying the two parts of this diagram together, right? Now, let's talk about the new stuff, because that's all stuff we've seen before. So what if you have a variable that depends on two other variables instead of one? So your picture looks like this now. Is it possible for us to say that z depends strictly on x? Z doesn't depend on just one thing, does it? It depends on two things, x and y. So when you talk about the derivative connecting these two, connecting the z to the x, you cannot talk about a straight derivative like from Cal 1. It has to be a partial derivative, meaning you have to hold the other one as being constant. So the only derivative that exists between z and x is a partial of z with respect to x. And the only derivative that exists between z and y is partial of z with respect to y. So if you have a single line connecting two variables, you can have a traditional derivative. But if you have two lines connecting, going from one variable to two different, then you can only have partials. Is that okay? So if we have this next example, where z is x sine of xy, then visually z here depends on how many things? X and y, right? Those are the only things it depends on. So there are only two possible derivatives, and they are what? Partial of z with respect to x and partial of z with respect to y. Those are the only two derivatives that make any sense at all. And we could do that, right? Do we need to? Or you could do that, right? Product rule there, and how about that one? We'll just do that one. I know you're telling me no, we don't need to, but what would this be? Sine xy plus cosine xy. What else? Xy on the outside of that. That's what the derivative of this would be, right? Now I want you to see something here. This derivative, this derivative is totally different than the one coming down this side, right? It would give us totally different results. All right. Next note. What if now you have a picture that looks like this? Your z depends on two things, x and y. But then the x you have depends on t, and the y you have depends on t. Can you hit the light in the middle? This might be, need to see this. There you go. Okay. So z depends on two things, right? But each of those two things depends on the same thing, doesn't it? So you could say that z ultimately does depend on just t, right? If I give you a value of t, that will produce the x's and the y's, and those will produce the z, won't they? So there is a direct connection between the z all the way down to the t. Now, what is the derivative that I can have between the z and the x? Well, because the branch splits off, right? It splits off in two branches. I can only have what type of derivative here? Partial. Partial of z with respect to x. Now, what about the connection between x and t? Is that a partial? That's a Cal 1 derivative, right? X is directly dependent upon t. So the derivative here is not a partial. It's what I'll call a straight derivative. Oops. Partial of x with respect to t, right? And what about down the right side? Partial of z with respect to y, and then how about from the y to the t? That's a straight derivative of y, dy dt, right? Now, going back to the last one we just did, we said that if z depends on x and y, right, then this derivative is completely different than this derivative, right? Completely different. We have to hold one of them constant and the other one as a variable. With this next one that we're doing, the difference is that we can actually talk about the change in z with respect to t, because z depends on t only. So it is possible in this problem for me to ask you what this is. That is possible. What is the change in z with respect to t? And what is it? I mean, that's what we have to determine. That's what this is about. What is it? Well, what was it with chain rule in Cal 1? What did we do down this branch? Like if we went down one branch like that, what did we do with those? Right there? When we went down a branch, we multiplied those two, didn't we? We multiplied those two parts of the branch together, and that became our chain rule. Well, same thing here. We're going to need to put these two together with multiplication. So I'm going to put that right here. It's partial of z with respect to x then times dx dt. But that only takes care of one branch. I need to come down the other branch also. And so I need this and this. These two need to be what? Multiplied again, right? Those two multiplied. And then how do I put the two branches together? I add them. And that's what the chain rule is all about here. I add to this, go down the other branch. Partial z with respect to y, then dy dt. Does everyone understand that the only reason that you can find this derivative and that it's a straight derivative? You understand me using the word straight? Okay, it's straight instead of a partial curvy d. It's just the straight d here. The straight derivative, or the normal derivative, why is it that that's not a partial?
Well, you're getting one input and then you get one output, so you just have the intermediate thing. And so,
do you have to hold any of those intermediate things constant?
No.
No, right?
It's a single input. The same input goes into both.
That's right.
And so, for the same input, you should get the same output, and that output will be determined by the partial, what you wrote up there, basically. Because how let me see how I can explain this. So,
well, you hold on. No, you already did it. Hold on. You have one input, right? That's going to generate an x, and that x is going to come in here and generate part of your z. This input's the same as this one, goes into the y, generates something that helps get z. But z ultimately relies on one thing only. Therefore, you could, like you said, intermediately, you could almost cut all this crap out and just say, hey, look, z ultimately depends on t, doesn't it? So it's the picture from Cal 1. That's a straight derivative. But in order to create that straight derivative, we have to take into account how it comes about. So we have to put in all this stuff. So we multiply the branches, right? Multiply down the branches and add the branches together.
oh,
That's what chain rule is saying.
yeah, that's what I was trying to say. Why you had to add, because you can't just put t in x or y. You have to put it in both simultaneously.
That's right. Z is going to rely on both at the same time. Okay, so let's take a look at, I think I have an example, don't I? Yeah. Oh. So what if z is equal to x sine xy, and let's say that x is equal to t squared plus 1, and y is equal to natural log t. What is it even possible for us to determine here? Well, let's draw a picture. Z depends on what variables? X right here and Y right there. So, you have X's and Y's there. So I know Z depends on X and Y. And then, what about my X? Well, my X depends on T's, doesn't it? I have to have T. And my Y also depends on T. So I can draw down and go T here, T here. So that's the exact picture I just had, right? So what derivative is it even possible for me to ask for? What's the only derivative I can ask you for? dz dt, right? That's the only thing I can ask you for in this problem. That's it. For you to get it, you have to create your branches, multiply, add them together, which we just did on the previous page, right? We did? Yes? Okay. So then if I already did this on the previous page, then let's get the answer. The first part was partial z with respect to x, wasn't it? What's the partial of z with respect to x? Sine xy, right? Product rule there, plus xy cosine xy. That part right there is just the partial z with respect to x. That's all this is right here. Times what? So I better put that in parentheses. Times what? the derivative of x with respect to t, the derivative, not partial, right? The derivative of x with respect to t, which is 2t, plus the partial of z with respect to y. What is the partial of z with respect to y? Well, x is now a constant, isn't it? So no product rule anymore? What's the derivative of sine of something? Cosine? So we have x cosine xy times chain rule. The derivative inside is just x, and that joins the x that was on the outside. So x squared cosine xy. That is our partial of z with respect to y. And then finally, what? Derivative of natural log of t is 1 over t. That's dy dt. Now, this would not technically be done. Are there any questions, though, on this? Technically, what we would like to do is, since our derivative says that z depends on t, right? We should get everything in here to have t's in it. So that means I'd replace this x with what? T squared plus 1. I replace that y with what? Natural log t. And then I do that everywhere in the problem. I replace all my x's with that and all my y's with that. And just, you don't have to simplify it or anything. Just plug in, you want your final answer to not have x's and y's. You want it to all have t's. So I'll show you what the first part of this would look like. If I was just rewriting that, it would be sine of t squared plus 1 times natural log t, and then plus, and I keep on going. Make sense? Therefore, your derivative, since it's with respect to t, t should be in here, and just t. Questions? All right, moving on. Now here's where the chain rule gets powerful. Let's say we have some z that depends on x and y again. But this time, x doesn't depend on t. X depends on two things, s and t. And the y also depends on s and t. Then if I were to try and figure out what derivatives are possible, does z ultimately depend on just one thing? Does it? No. Z ultimately depends on what? Two things, right? S and t. So what are the only things that would be possible for me to even ask for? Partial of z with respect to s, and the partial of z with respect to t. Do you see that these are the only two things that are possible? If z ultimately depends on s and t, those are the only two things that I could ask you for. But I cannot ask you for a straight derivative, dz dt, right? The only way you can figure out the rate at which z is changing with respect to t is if you hold s constant, or vice versa. So the way we're going to do this, if these are the only things we can actually find, we need to actually figure out, how you get this from this picture. So since z over here, right, depends on two things, the only thing possible to connect z to x would be what? Partial, right? The only way to connect z to y would be partials. But then if I try and get from x down to s or x down to t, since x depends on two things, the only way I can go is with partials again. So I go partial x, partial s, partial x, partial t, right? And then over here, what do we have? on the y, partial y, partial s, partial y, partial t, and that's it. I realize this is all drawn out for you, right? It's all there, but you need to be able to come up with what we call these tree diagrams, all right? On a test, you'd be expected to draw the tree diagram and then generate the derivative that I ask for. So like in a test, I may ask you for, the instructions may be just, giving you the functions and then asking you for just this, partial z with respect to t. That's all I want. So how would I get that from here? Well, I need to multiply down, right? Multiply the tree branches together. But because I want with respect to t, what I need to do is start out at z, come down the branch, get myself to x, and then go to t down here. So I follow that branch down. And then I have to also, since there's a t on this one, I need to go down that branch also. Come down like this, come down, and get all the way down to t. So the derivative, the partial derivative of z with respect to t will be equal to multiply down this branch, partial z with respect to x times partial x with respect to t. Then what? Add, so go to the other branch, partial z with respect to y times partial y with respect to t. See how that works? And that's it. That would be for partial z with respect to t. Now, had I asked you for partial z with respect to s, you would go down this way and then down that way to s, and then you come down here and then down there. See the difference? So what would change if we wanted this one right here? What would change in our formula? What would be the only thing that changed? This right here would be with respect to s, and this one right here would be with respect to s. Okay, let me draw one up here. I'm kind of going to deviate from the notes for a second. What if z depended on x, y, m, x and y, or x depended on t and s, y depended on t and r, and m depended on t? My question to you is, what derivatives are even possible for me to ask you for? Hold on. Partial z with respect to t, is that what you said? What else? Or is there anything else? Partial z with respect to s, anything else? Partial z respect to r, anything else? Yeah, well, that's kind of the intermediate part of it, though. In terms of z, ultimately, z depends on one of these three variables, right? Right? So any of those three would be possible. Let's just focus our attention on well, let's do this one right here. So what branch would I go down here? Go z to x, right? And then go to t, right? Tell me about those derivatives. Partial z respect to x, then partial x respect to t, right? Do you agree? Okay. That wouldn't be the only thing, though, right? I would now need to go down z to y, and then y to t. So I'd have a couple of partials here also. Partial z respect to y, partial y respect to t. What about the last branch? Do I need to go down there? Yes. Go down here, go down here. So that would be partial z respect to m, partial m with respect to t. That's a great question. That's what I was about to ask you. What kind of derivative would this be? So let me give you an example. Let me give you an example of an m. Okay, let's say m was equal to t squared. Does everyone agree that that m is dependent on t only? Yes? That's right. The partial will still work. Now watch. What if I say plus 0r plus 0s? I mean, that's now all you're doing is saying, yeah, m depends on t, yes, but you could also say it depends on r and s, but the r and s really don't do anything, right? There's no contribution to the r from the r or the s. So you could, even though my branch does not have the r and the s there, I could throw the r and the s in here, and it wouldn't change the fact that that partial of m with respect to t is still going to give me the same answer as the straight derivative would have. And look at over here. Could I have thrown an s onto this branch over here? Wouldn't have changed anything. Could I throw an r into this one? Yes. So for that last part, you could either do a partial or you could do it as a straight derivative because it won't matter. So what we're supposed to do now is we're supposed to take this one and this one, multiply them together, right? Then plus down this branch, plus down that branch. Add all those up, that's your derivative. And that's just that first one, right? If you want the next one, you have to redo it and go down different branches. One more picture. What about this? Z depends on x and y, which depends on t, which depends on r and s, which depends on r and s, which depends on q, 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 q. What derivatives are possible? dz dq. It's the only one possible, right? Ultimately, z depends on q. And it's going to be a lot of stuff put together, isn't it? What about this derivative coming down this way? What's that? Partial z respect to x, straight down here. This can be dx dt. Come down here. Partial t with respect to r. Come down here. dr dq. And then you have to go and let's see. The only other branches I've got on here, I've got to come here, right? And down here. Like that. Pardon? Wait, partial z, partial y, dy dt. Correct. Yeah, you could. I'm more just paying attention to the branches. That's all. I'm not even. And then over here, dr dq, s dq. Right. I missed one here. It was partial t with respect to s. ds dq. Okay. So what would the derivative be? Shit. It'd be this, right? Times that. Times that. Times that. That's down one branch. Then plus, and then you have to come down the other branch. And then you have to do plus, and then you have to go down the other two. It's really just more of, like, do you understand the methodology of it? And how really you could have one quantity depend on multiple other quantities, and those be connected to each other in different ways, and somehow, at the end of it all, be able to say, what's the instantaneous rate of change in Z with respect to Q? So let's say that you had that Z represented the probability of rain right now, right? Today, right? The weather guy gets up there, weather lady, whatever, gets up there and says, oh, we got 41% chance of rain today. Well, what do you think that probability comes from? Well, probably a bunch of variables, right? And each of those, like, you know, they somehow say, oh, this is going to be the humidity, this is the temperature, this is the pressure, this is blah, blah, blah. They've always, oh, well, how do they do humidity? Well, humidity is a function of these three things, and maybe perhaps that one's a function of two. So they've got all these things, right? At the end of the day, they want to know, like, you know, what's the rate of change of that? How is that probability changing right now? Well, it's going to be a bunch of differentials put together somehow. How do you connect them together? Well, you do it with this sort of tree, the chain rule. Make sense? All right. What do we have? Is that all we have in there? I give you the general case. Oh, no, we've got a couple of formulas. Implicit differentiation. I'm going to kind of skip through the implicit and just do an example to show you how the implicit would work. I don't know if you remember in Cal 1, but in Cal 1, you were given a formula for implicit differentiation. Not many people use it, but it's there. And it's kind of the same thing with these. So look at 11.5.7, the note, and just where it says, I think there's a typo. Let me see your notes. I want to see who has their notes here today. Are these in? Let me see if there's a typo in here. With respect to Y, I did fix it there. Is that the only thing you have there? Is this all on backwards in here? It's backwards, isn't it? Is that what it is? Okay, it looks all weird here. That's all you want. Okay, good. I have an older version of the notes. I want to make sure it was corrected in here. Okay, so there are two formulas. One of them is on the 11.57 where it says continued. So the formulas we have are this, and I'm just jotting them down up here. Partial Z with respect to X equals negative partial capital F with respect to X over partial capital F with respect to Z. Everyone see that formula there? Yes? Okay. Here's the way this works. There's another formula on the next page that shows you the formula if you want to go partial with respect to Y. But do y'all see the typo on there? Oh, it is fixed on here. Okay. No, never mind. Never mind. Okay, we have that one. Let me put them both up here to make sure nobody has the wrong version of this. What do you have for that one? Do you have the one that says Y on it? Does it say negative partial F with respect to Y over partial F with respect to Z? So you have two different formulas, right? That's the way they look? Yes? Okay. Good. So let me show you how this works with the next example. If you have x cubed plus y cubed plus z cubed equals 6, I did that again, plus 6xyz equals 1. Does that look familiar? Does? I realize we're due for a break here. Hold on. We're not breaking yet. We did that problem earlier, didn't we? Is that one right? Oh. Is that one right there, right? And I stopped and said, okay, you can isolate that and solve, and we were done. Well, here's the way it's going to work now. Okay, the first thing that we have to do is we have to move everything on this equation to one side. Okay? And notice we have three variables, x, y, and z. It would be hard for us to solve for z, wouldn't it? Be hard for us to solve for z. But we could ask ourselves, what's the partial of z with respect to x? We could ask ourselves, what's the partial of z with respect to y? So let's move everything over. If I move everything over, the equation actually becomes minus 1 equals 0, isn't it? I will call everything on the left side of this equation capital F of x, y, z. Now go to the formula 7.57 where it says continued. The very top it says capital F of x, y, z equals 0. You'll have that? Suppose we want partial z with respect to x. All we have to do is this right here. So what is the partial of capital F with respect to x? So all I'm doing is focusing on this side of the equation. What's the partial of that with respect to x? 3x squared. Then what? Everything else? If I say partial of f with respect to x, what am I treating like constant? X and z, right? Both x and z. See, that's the key. If I'm doing this partial with respect to x, I'm looking through here, I'm treating everything like a constant except for x itself. So I get 3x squared what? Plus 6yz. That's your partial of capital F with respect to x. And then let's do the bottom part, which means we need to do the partial of f with respect to z. So what's the partial of f with respect to z? 3z squared plus 6xy, right? And so my answer is the ratio of those two with the negative out front. So the partial of z with respect to x, my final answer is negative 3x squared minus 6yz all over, was it plus? Yes, thank you. Plus 3z squared plus 6xy. Wasn't that much easier than the other way, right? You can go through the, how these formulas are derived if you like. It's in the book and it's kind of in the notes a little bit. But they're so easy to use. It makes the way we did it earlier kind of like, no, you don't want to do that. Was it right here? You can kind of see it though in here. If you take this term right here and this term right here, okay, what are the terms that are left other than those? We would have a 3y squared and a 12x, something like that. You take it to the other side. Then you divide through by what? After you factored out this. 3z squared plus 6xy. Should match up. Let's take our break. I'll check to see that it matches, but let's take our break right now. 2:55. Let's come back at 3. We still have more to do, don't we, today? You should be able to do everything through 5C now. So you'd be able to do all of this except for 6, 7, and 8. All right, we ready to keep going here? No? Call it a day. See you later. All right, let's, if you don't mind, Allie, maybe hitting that middle light for us. All right, you may recall that when we first started talking about partial derivatives, the idea was that we were walking along the surface, walking along some surface, and then we aimed ourselves in a certain direction and cut our surface, and it created a curve. Do you all remember that picture I had up here? That curve we could find the tangent line of? It's been a whole week. Let me see if I have my other picture up here. Trying to figure out where the hell my code is here. Here we go. Can you all see that okay? We have a surface. I'm going to take this plane out of here. Make this a little bit smaller. Okay, do you remember that picture kind of now that I have it up here? We had a point that lived somewhere on a surface, and when we said the partial with respect to x, right? The partial with respect to x, we held y constant. Y being a constant was basically meant that we had a plane that would cut this thing, right? So we would cut this thing with a plane. Everyone agreed that that plane, if the y-axis is right here, this axis, that y is being held constant, that's that plane, it creates this curve, and then we can talk about the tangent line there, which would be this blue line. Take that surface out of here. Yes? The direction that I was pointed in, okay? So when I'm standing here on this function, I was pointed in a direction that was down that plane, right? So I was parallel to which axes? The x or the y axes, if I'm standing there on the function. Which one am I parallel to? Parallel to the x-axis, right? So my direction is parallel to the x-axis. Now if I cut it the other way, which means I want to hold x constant, then I'm going to be pointed in a direction that would be parallel to which axis instead? The y. So let me try and bring that back in here. Take that plane out. Now, notice on the ground, if I look at this surface from the top, that red arrow is representing the direction which I'm pointed. So I'm pointed in the same direction as that red arrow, and that's parallel to the x-axis, right? Y-axis, thank you. So if I come in here and cut this with the plane now, that way I get my slope of my tangent line right there, and that's my partial with respect to y, right? You see the difference between the two. So partial with respect to x, I'm pointed parallel to the x-axis. Partial with respect to y, I'm pointed parallel to the y-axis. With me? But there's nothing that says I can't point in any direction. We had talked about this in the very beginning. Remember last class you even mentioned that. Why go parallel to one axis or the other? So if I look at this from the top again, I've got that plane where I've cut it, right? What if I decide to spin this guy around a little bit and point him, I don't know, point him right there, that way? Then I still have a curve of intersection, don't I? I still have a curve that intersects my surface. And it makes perfect sense to talk about the slope of a tangent line on that curve, right? And I can spin that thing around however I want. Bring it over this way too. So again, I'm not pointed parallel to any of the axes now, am I? And so what we have in this section is a more general concept of a partial derivative, and it's called the directional derivative, right? The directional derivative. And we have a formula for it. So keep in mind that red vector on the ground, that red vector is a vector that represents the direction in which I'm pointing, right? We call this like a direction vector. The question would be, what's the slope of the tangent line when I'm standing on that curve pointed in that direction? What's my rate of change? And that's what we're doing. So the directional derivative, we looked at the surface, right? We can pick any point in the domain, and we'll be standing on the surface. At that point on the surface, we can point in any direction we want. In that direction, there is a tangent line. The slope of the tangent line will depend on the direction that we're pointing in. If z is a function of x and y, so z is a surface, then f has a directional derivative in the direction of the unit vector u equals ab. So remember that red vector that was on the ground? That red vector? That's our unit vector u. What does unit vector mean? Magnitude 1, okay? Magnitude 1. The unit vector that gives you your direction must be a unit vector, must have length 1, must be unit, in order for you to use this formula. So if u is our direction vector, right, our unit vector that's pointed in the direction, then here's the derivative with respect to u of our function f of x, y. It is a times partial of f with respect to x of xy plus b times partial of f with respect to y, partial of f with respect to y at xy. Okay, this answer is a number and represents the slope of the tangent line and surface in the direction of the vector u. Now, let's talk a little bit about this before we do this example. This formula that we just got. The derivative in the direction u of f of x, y is equal to a partial f with respect to x plus b times partial f with respect to y. So check this out. Let's say we're looking down on the domain, okay? And we pick some point. Let's say I pick a point right here. So there's a surface above this, right? I'm standing there. And what if I tell you to point in the direction that's parallel to the x-axis? Parallel to the x-axis. That would be either in that direction or in that direction, wouldn't it? Somebody give me a unit vector that points in one of those directions. I, right? That's the same as 1, 0, isn't it? Yes? That's 1, 0? And that means that A is 1 and B is 0, isn't it? Now plug A is 1 and B is 0 in here, and what do you get? The partial of f with respect to x, right? You get the partial of f with respect to x. And didn't we say that the partial of f with respect to x is the derivative when you are pointing in the direction of the x-axis? That's why. Because when you're pointing in the direction of the x-axis or parallel to the x-axis, your y component is always 0, and therefore that second part of the formula will always be gone, which means it's the partial with respect to x. What I'm trying to get at is that this directional derivative is a generalization of the partials. That make sense? What if I said, okay, instead of pointing that way, point parallel to the y-axis? Well, now you'd pick a u. How about j? Right? 0, 1. That points you up. That's a unit vector, right? Both of these were unit vectors. And if I plug in 0, 1 for A and B, you get partial with respect to y, which is exactly what we said would happen if we point in the direction parallel to the y-axis. What this formula allows us to do is point anywhere in between those, all right? Anywhere we want. Was there a question?
So, yeah, so basically weight each partial derivative by the percentage of the direction you're pointing.
You could say that. It scales the partial derivative of f with respect to x or y by basically the magnitude of that component of the vector, right? The bigger this component is, the more of the partial with respect to y comes into play, right? The bigger this one is, so it's like a weighted.
And it's always number between 0 and 1.
The magnitude of the entire vector cannot be more than 1, right?
Right.
Yeah, so each component by itself can't be.
Right. So I see. Yeah. So
Scaling it. Okay? Now with that, let's go ahead and do this example. All right. We have f of xy equals x cubed minus 3xy plus 4y squared. It says if we have this surface, then find the directional derivative at the point 1, 2. So I'm given a point 1, 2. And in the direction of a vector making the angle pi over 6 with the x-axis. Okay, so if I'm looking at the domain, right, I'm standing at the point 1, 2, and I'm up on the surface somewhere, right? Or I'm on the surface. You can't see it here, but I'm on it. I want to be pointing in the direction where I have an angle of what? Pi over 6 with the x-axis. So I want to be pointed in the same direction as that vector right there, where that angle in here is pi over 6. And it has to be a unit vector, doesn't it? So if the length of this vector is 1, then we may as well look at it as being on the unit circle, right? And what are the coordinates of the unit circle? The point right there at pi over 6, 30 degrees. Root 3 over 2, 1/2, right? You could also just say, how long is this side, and use trig, right? Cosine is adjacent over hypotenuse, cosine of pi over 6, and just work out that side on its own, right? If you didn't know it was if it wasn't a nice angle, in other words, that you can recover the points easily, you could just use your knowledge of triangles to get the coordinates. So what is the vector u? What is the direction I'm pointing in? What is this u vector? It's the vector root 3 over 2, 1/2. You understand that? Okay. So what else do I need to come up with my directional derivative? Some partials. Let's go ahead and grab some partials. What's partial of f with respect to x? 3x squared minus 3y. Partial of f with respect to y, negative 3x plus 8y. Y'all agree with those? Anyone disagree? Agree? Okay. So let me write down what my directional derivative is. My directional derivative in the direction of u of f of xy should be equal to a, which for me is square root of 3 over 2, times the partial of f with respect to x, plus b, which for me is 1/2 times the partial of f with respect to y, which is negative 3x plus 8y. That is the directional derivative in the direction that I was given. Now all someone needs to do is give me a point, right, an x and a y, and I can tell you exactly what the slope of that tangent line is. And that's what they gave us, right? Did they give us an x and y? Yeah. They gave us the 0.12, right? That's where I'm standing. So the 0.12, just plug in 1 for x and 2 for y and figure out what this is, and it's a number, and that's your slope. Okay? I don't think I'll do that, but plug in 1 there and 2 there and 1 there and 2 there and figure it all out. Questions? All right, what's next? If z is natural log x squared plus y squared, then find the directional derivative at the point 2, 1, and the direction of the vector u equals negative 1, 2. Ready? We have natural log x squared plus y squared. I have the point 2, 1. And what's the vector u that they gave me? Negative 1, 2, right? Okay. So I'll need some partials, won't I? Let's grab those partials. F, partial f with respect to x will be 2x over x squared plus y squared. That's because the derivative of natural log of something is 1 over it, right? Times the derivative of what's inside of the natural log with respect to x is just 2x. I'm not there yet. Yes, I'm glad you said that, though. Here's our partial with respect to y. I was intentionally leaving that part of it out, hoping that y'all would forget. My directional derivative in the direction of u. And can I use u? Yeah, see, u is not a unit vector, right? U is not a unit vector. How do you know it's not a unit vector? Well, what's its length? It's not 1, right? So the only way to, if you use u right now, if you use u and you say, okay, u, and then f of x, y, and you come in here and put, okay, negative 1 in front of that first partial like this. You understand what I'm doing right now? And then you say plus 2, and then whatever, the rest of it. Then you're basically going to lose like 8 out of 10 points for that. Because this is not even close to the right directional derivative. Yes, you took derivatives correctly, but the thing that I see that most students overlook is that the direction vector has to be a unit vector. This formula doesn't work. And I believe, without saying too much, but I mean, I think I've already almost given this away now. 6a, find the slope of the line which is tangent to the following surface at the given point and in the direction of u. Last spring, I don't know how many people used that u. That u is not right. You have to do something to it, right? What do you do it? What do you scale it by? Its own length. So find the magnitude of u here, which is square root of what, 5? So the u that you're going to use is not that. So let's not call it u. How about that? Let's call it something else. Why don't we call it v? Let's use the vector v, and we'll say negative 1 over root 5, 2 over root 5. Now, is that a unit vector pointing in the same direction? Yes. So instead of coming over here and saying directional derivative in direction of u, I'll just say v. And then I'll switch these up, and these will just be negative 1 over root 5 and 2 over root 5. And now you're in business, right? Now you're in business. You can use these. And then you want to plug in 2, 1, don't you? 2 for x, 1 for y, and then figure out the answer? Questions? Kind of a little off topic here, but let me ask you something. And if you know, if I've already explained this to you, if you've had me before in a previous class, just hold tight. Don't give it away. Does everyone agree that these are the same? Right? Now, the only difference is that on the left side, you know, they'd say you have not rationalized the denominator yet, right? So to get from here to here, what do they tell you you need to do? Multiply top and bottom by root 2, right? And that gives you the rest, and then you're off, you know, whatever. Everyone's happy, right? How many of you were told that you always need to rationalize these things? Anyone ever told, like, almost like they shook you and like told you, do not leave the square root in the denominator, you know, right? I was taught the same thing. And then I learned at some point why. And when I learned why, I got all pissed off. So that's why I'm going to share it with you. Okay, so look, check this out. Before calculators, before computers, right? Back in the old day, like slide rule day, where they carried slide rules on them. If you were asked to calculate this and get a decimal approximation to that, then how the hell would you do that? Well, you would first have to, there were certain numbers that you had to kind of know. Like before calculators and computers, it was actually a sign of your mathematical intellect. It's how many weird numbers you knew and how many decimals you knew them. So like I have a colleague here who's in his 60s, and he knows pi out 120 digits. I mean, just you can go up to him right now and say, what's pi? Go out 120 digits. He can just 3.14, blah, 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 blah. And that's because that used to be the measure of like how smart you were, I guess, at some point. Or, you know, that was like the cool thing to do back before computers. All right, what's square root of 2 out 30 places, you know? Well, you know, and so that was like a cool thing to know. Well, there were certain numbers, everyone, you know, how many times did we come across square root of 2? A lot, right? So all the students back before calculators knew what square root of 2 was, approximately a few digits out, right? Anyone know what square root of 2 is, a few digits? 1 point, I think it's 414. Yeah, whatever. So there it is, right? We have calculators now, so we're not cool like that. So 1.41. So students would know what 1.41 is. You know, they would know what square root of 2 is approximately. All right, so now they have to do 1 divided by square root of 2. So if you look back, I mean, again, no calculator. So they go old school division, right? So how do you divide 1.4 divided by square root of 2? I mean, sorry, 1 divided by square root of 2. You put the square root of 2 on the outside of the box, right? And inside the box you have the 1. And then you start doing decimal division. So you say, okay, 1.414 doesn't go into 1, so you add a decimal, right? Bring this up. How many times does 1.414 go into 10? About 7 times. And then you do your multiplication, you come through with it, right? Do you see that's kind of, ugh? Now, rationalize the denominator instead. If you rationalize the denominator, look at what this division is instead. It is, what's on the inside of the box? 1.414. What's on the outside? 2. Now, 2 doesn't go into 1. Carry your decimal up. Does 2 go into 14? Yes, 7 times. Carry it down. You see how much easier this division is than this division? You see the difference in the divisions by hand? So much easier to do this than it is to do this. And that's why they did it. Now, that's a skill. Now, we know if it's like variables and stuff, we always need to know that we can rationalize denominators. But anytime anyone has ever told you, like, no, that's wrong because you left the square root in the bottom, come on, seriously? It's the right, I mean, they're the same number, right? Same number? So that always kind of irked me a little bit. So I like to sometimes share that with people, that when people tell you to rationalize a denominator, it's usually because they were told to do it. You know, it's never really like, there's not a good reason for it other than if you ever have to do it by hand, you'll have a better time with it. So, all right. I can't. Okay, so what's the moral of the story here? I mean, as far as this problem was concerned, the thing you have to pay attention to, unit vector, right? Your direction needs to be length 1. Okay, now that leads us to very, very important concept, all right? The gradient vector. Have you ever heard of the gradient vector? Right? Gradient is like, when you think of a gradient, you think of like, you look at a hill or something, they talk about gradients, like the pitch of the hill or something like that. Well, it's very much connected to the directional derivative. In this formula, for the directional derivative, we have a number in front of our first partial with respect to x, and then another plus another number in front of our other partial with respect to y, right? If I wanted to, right, if I just got a whim, I could rewrite this part, right, this partial of f with respect to x, partial of f with respect to y, as a vector, right, whatever that is and whatever that is, just put it in angle brackets, and then I could say dot that with AB. AB are just two numbers, right? Put those in angle brackets. Remember, the definition of the dot product of two vectors is you multiply this one, this part, times this, right? So that would give you this. And then you would say plus, then you do this part times this, and that would give you this. So, I mean, it's just, I could do that, right? So we could look at the directional derivative as the dot product of two vectors. And here are the vectors. It's this vector dotted with this one. So if the directional derivative can be seen as a dot product, any question on the notation there? Then the gradient vector is defined and written to be, this is the gradient symbol, it's actually the del symbol. Okay, del f of xy is equal to the vector, which is the partial of f with respect to x, partial of f with respect to y. So it's this piece right here. That right there is the gradient vector. So these are the notations. So it is a vector determined by the partial derivatives of the function. So what's the gradient vector for that? What's the gradient of f here? This will just be an exercise in taking partial derivatives. If f of xy is e to the xy cosine x plus y. You're asked to find gradient f. The gradient of f is a vector. It's the partial of f with respect to x. What is the partial of f with respect to x? What's derivative of e to something? Is that's the same thing, right? E to that something, but then you have to take derivative of what's up there. What's derivative of what's up there with respect to x? Y. So you get y e to the xy plus, what was the derivative of cosine of something? Negative sine of that something, and then times the derivative of what's inside. What's the derivative of what's inside? Well, because we need to know. It's, I mean, you got to find any glimpse of humor, even if it's just terrible humor. It has to be, you have to utilize it sometimes. Okay, derivative of what's inside of that is what? Just y? No? Just 1? Right. What is the derivative of x? With respect to x, it's 1. And plus derivative of y, well, y is a constant, so that's 0, so you just get 1. Now, that's just that partial with respect to x, right? That is the first component of the gradient vector. The second component of the gradient vector is the partial with respect to y. So we should get x e to the xy minus sine x plus y. And then that same thing, a 1 pops out there also. We all agree with that? That's our gradient vector. What if I take that and I dot it with a unit vector? What will that represent? The directional derivative, right? As long as that vector is a unit vector, right? It's a directional derivative. Now, things are going to get really cool here, I think. So, no questions there? We can extend this. All this note is basically we can extend this out to three-dimensional space. Okay? So if we look at a function, our function depends on three variables instead of two. So if I have a function of x, y, and z, is that a surface anymore? Sometimes they're called hypersurfaces because they're in a fourth-dimensional space. But generally speaking, we no longer have the nice carpet floating in the wind type thing that we have with a function of two variables. So, but if we do have a function of three variables, we still can get a unit vector. It's a three-dimensional unit vector. And we can still define a gradient to just be the partials, but now we'll have three partials instead of two. Right? Everything's still the same. That derivative might be interesting. Shall we? F of x, y, z is x over y plus z. I'm more curious to see how you would take that derivative. What's the gradient vector? Well, the gradient vector is the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. Those are the three components of the gradient vector. So what is the partial of f with respect to x? 1 over y plus z? Now, I'm going to write down f down here just to kind of help us out a little bit, just in case we get hung up on it. That's just rewriting what f is, right? Bringing that y plus z up. If I say what's derivative of this with respect to x, all of this is a constant. Derivative of x is 1. So what's all of that? Well, that's just 1 over y plus z. Right? Okay, what's the derivative with respect to y? So that's a constant, right? What's the derivative of this? Well, that's chain rule. Negative 1 has to come out, doesn't it? So the partial, I'll write it down here. The partial with respect to y. The negative comes out in front of the x. And then I have y plus z to the negative 2, right? Because I have to subtract 1, power rule. And then the derivative of what's inside. What's the derivative of what's inside with respect to y? 1. So that's it. So we have, how about this? Negative x over y plus z squared. See, this is somewhat of a non-trivial derivative. You have to understand a little bit about power rule and chain rule. How about the next part? What's the partial of f with respect to z? So it's the same thing, isn't it? Same as this. So negative x over y plus z squared. And that's your gradient vector. So in order to find the gradient vector, you need to be able to take the partials, right? What's the directional derivative at the point 4, 1, 1 in the direction of the vector u, 1, 2, 3? So what would the first thing you need to do be? To turn u into a unit vector. So scale that vector by its own length. And then you could dot that, couldn't you? I'll go ahead and finish out this problem. I'll need this. My u vector is going to be that vector I just had. It was 1, 2, 3, wasn't it? But I'm going to scale it by its length. What's its length? Root 14? And rationalize it, right? Hell no. We ain't rationalize that. So the directional derivative in the direction of u. Notice I've renamed u. Okay, I should have used v because the u I was given was 1, 2, 3, right? I'm calling u this though. So without loss of generality, I just keep it like that. So this should be 1 over root 14 times what? I'm doing the directional derivative now. Yeah, times the x component. Good. And then plus 2 over root 14 times the y component. And then finally 3 over root 14 times the z component, which was the same as the y component. And then I'm supposed to plug in numbers, right? What was it, 411? Yeah, 411. I'm not going to, but you could just plug in 4 for x, right? 1 for y and 1 for z. And that's going to give you a number, right? And that represents the, oh, what the hell does that represent? Yes and no. Because do you have a tangent line anymore? See, because this is a function of 3 variables now, right? Well, it's the, okay, look at it this way. What did the slope of the tangent line geometrically represent for us? Like when we had this, you come over here like this, we have x, we have y. This right here was dy dx, wasn't it? dyx meant the instantaneous rate of change in y with respect to x, right? So if you're standing there and you're at this point, and if you try and move along that curve to the right, it's telling you the instantaneous rate of change in that direction, isn't it? Now what about if I go to the left instead? Does that change that slope, or does that change the derivative's value? You would say in one direction it would be increasing, the other direction would be decreasing, right? But it would be the same magnitude. So in this case, this is saying, do you remember when I was talking about temperature in the room, right? So in three-dimensional space, I'm sitting here somewhere. Let's say I'm at the point 411, sitting here in this room. And let's say that this function, f of xy, which was up there somewhere, tells me the temperature, the different temperatures in different places in this room. Then the directional derivative in the direction of that vector is if I went and pointed to that vector, whatever it is, right like that. Let's say that that's the vector 1, 2, 3, and it's been scaled to be a unit. If I go and take a step in that direction, then this value represents the rate of change of temperature. So instantaneously as I move, the temperature is trying to change by that amount. Got it? So it doesn't have to be tangent line anymore. In fact, if we're in this three-dimensional sort of space, then it doesn't necessarily have a tangent line. Okay, where's my thing there? I think I lost it. We only have an hour left. Did we get out at 4:30 or 4:40? 4:30? Oh, never mind. We have less than. So my other class ends at 4:40. Can you do 6A? Yes, we said you could do 6A already, right? But you can't do 6B yet. We are going to get out of here, and you will be able to do 6B. Okay, this is really cool. Check this out. We said that the directional derivative was the gradient dotted with the directional vector, right? The gradient dotted with the directional vector. Remember this formula for dot products? U dot V is magnitude of U times magnitude of v cosine of the angle between them. Yes? Now, if we look at the directional derivative, directional derivative, we have that the gradient is dotted with u, which means that if I take the gradient and dot it with u, it should be equal to the magnitude of the gradient dotted with the magnitude of u cosine theta. But that's magnitude of gradient cosine theta. Why? Because the magnitude of u is 1, because it's a unit vector. So this is just this. The largest this can be is when cosine theta is 1, right? The largest that cosine theta can ever be is if it's 1. What's the angle that I would need in order to make that 1? 0. And this is the big result, which means the angle between the gradient of f and u must be 0 to attain the largest directional derivative. This is an absolutely fundamental result of today and Cal 3 in general. So again, let's say I'm this person in three-dimensional space, and I'm trying to figure out, I've got a function that tells me the temperature everywhere in space, right? And I'm trying to figure out which way should I point so that I have the maximum or largest instantaneous rate of change, right? Which way do I point? Well, I can point in any direction, call it u, right? And I could say, go that way, what's the rate of change? Go that way, what's the rate of change? I can go any way I want to. But this tells us that the direction that you need to point is actually the gradient. Because what it's saying is that the angle between the gradient and your direction has to be 0. So if I'm just moving around in space, I have a gradient vector no matter where I am. The gradient vector is defined because it's just the partial derivatives, right? So everywhere I'm at, I've got a gradient vector. There it is. It's sticking around. As I move, the gradient moves around. Okay, and then I get to a point, and I'm stopping there. I say, okay, now where do I go to get the maximum rate of change? Well, guess where you go? Same direction as your gradient vector. If you point somewhere else, you've opened that angle up bigger than 0, so the directional derivative will be, the magnitude of that thing will be smaller. We have to keep that angle 0, so you want to keep pointing in the direction of the gradient. Is that okay? Big time result there. So maximizing the directional derivative. The maximum value of the directional derivative is the magnitude of the gradient, and it occurs when we point in the direction of the gradient. So here's a surface, okay? Here's a surface. So this is two-dimensional domain. Surface is up there. And I'm going to try and do what? Find the direction as an angle of the maximum rate of change at 0, 0. Okay. What should we do? If we have function 2 variables, I want to find the direction as an angle of the maximum rate of change. Okay? Maximum rate of change of this function at 0, 0. Sine x minus y plus cosine x. So what is the maximum? And find the direction of the maximum rate of change at the point 0, 0. So in my domain, I'm sitting here at 0, 0, right? And I'm saying to myself, which direction do I point in, right? So I get maximum rate of change up on that surface. According to what I just said, it'll be in the same direction as the gradient, won't it? So I just need to find the gradient. What's the gradient? What's the partial of f with respect to x? Cosine x minus y minus sine x. That's your partial with respect to x. What's your partial with respect to y? cosine x minus y times -1, because you got a little bit of chain rule there. Those are my two partials. And now I want to know what's happening at 0, 0. So the partial, the gradient at 0, 0 will be equal to, well, what's cosine 0? 1, sine of 0, 0, so I get 1, and then cosine of 0 is 1, so that's -1. It wants the direction as an angle. So I'm at 1, pointing out 1, -1. So like this, right? That's where I'm that's the direction I need to point right here. So you could say -45 degrees, or you could say go the other direction, doesn't matter. Negative pi over 4 would be my angle. Now, the other part of the question says, for us to find the actual maximum rate of change. So find it. What is it? And amazingly, it's just what? The what? The magnitude of that vector. The magnitude of the gradient vector at 0, 0, which is the magnitude of this vector, which is the square root of 2. Yep. So do you all understand what's going on here? You've got this surface, right? Three-dimensional space. And we're looking at, let's say, this is x-axis, this is y-axis. Here's the origin. We're up here on the surface, right? And we ask ourselves, okay, which way should I point so that when I go that way, I get the most rate of change? According to this, it says we need to point in the direction of 1, -1. So again, if this was x-axis, this was y, I need to turn 45 degrees this way and then head that direction. If I head that direction on the surface, I'm going to start increasing. And how much will I be increasing by? What's the instantaneous rate of change? 1.414, square root of 2. Okay? It's amazing that you have all that information, right, from just knowing what the function is. You don't have to do anything else. You just have to be able to find its gradient and then take its magnitude. That's it. And you know the steepest ascent. Okay? Okay, example 6 and 7 are going to be an in-class quiz. Yes! We're going to get our first one in today. Yes! Y'all can work together. Let's knock it out, okay? You're going to turn it in on a separate piece of paper so everyone does their own work, but you can talk, you can help each other. That doesn't mean just copy your neighbors because you have no idea what you're doing. That means help, ask for help. Everyone's turning in their own, yes. So you're not going to turn in like a group quiz. Everyone has to have their own copy to turn in with your own work. This will be all we do today. Example 6 and 7 to be turned in. I should probably tell you that on your take-home exam, you are not going to be able to do number 7 and 8 yet, okay? You should be able to do everything through 6, though.